In the last movie, we talked about bending stresses in beams, where the bending stresses were due to the moments on the beam due to loading, and bending stresses were also at their maximum value at the outer fibers. Now I want to talk about shear stresses in beams. Okay, in this cartoon here, we talk about a simple beam, kind of like the whole deck of cards. And when it's loaded, you see how these ends kind of not match up anymore? Essentially what's happening is we're causing shear stresses between the layers in that beam. It's really what's happening. So when we consider a beam, this is deriving the general shear formula. So they're looking at a section taken of beam that's subject to shear. You have the shear diagram and then the moment diagram, and I'll let you follow along in your textbook, but the general shear formula is in equation 14.8. We're giving the shear stress the symbol FV, small fv. That's the horizontal and vertical computed shear stress at any given plane. That equals V times Q divided by I times B. V is the computed vertical shear force at any given section. Q is the statical moment, and we'll talk about the statical moment in a minute here. About the neutral axis of the cross-section area of between the horizontal plane where the shear stress is to be calculated and the top or bottom of the beam. We'll show you what that means. And then I is again the moment of inertia for the entire cross-section that is. And then B is the width of the cross-section in the horizontal plane where the shear is being calculated. Okay, so this equation is particular to the position at which you're calculating the shearing stress. Shearing stress will actually be at its greatest at the neutral axis and be at a minimum at the outer fibers. So let's talk about the statical moment. Statical moment Q. Q equals actually the sum of A times Y bar, where A is the area above or below, depending on where you're at in the beam, the area above or below the plane where the shear stress is to be found. Okay, so what you're trying to do is you're trying to find the shear stress at a particular plane. And then Y, or Y bar, is the distance the centroid of the area A is to the neutral axis. And we'll talk about that in a minute. We can also express this shear formula as an allowable shear formula, where capital FV, that would be the allowable shear stress, and then VR is the allowable shear force. Okay, so we've done that kind of equation before. Let's talk about the statical moment again. Okay, so this cartoon shows up in your textbook. Okay, so in this particular case, what we're trying to do is find the statical moment about this arbitrary plane G. Okay, so we have a neutral axis right here. Okay, and remember I said the statical moment is the area times Y bar. So in this case, what we're trying to do is we're trying to find the shear stress at this arbitrary plane shown right here. Okay, so A would be the area above that shear plane. So that's the shaded area you see here, which would be B times D, and then times Y bar, and Y bar is the distance from the neutral axis to the centroid of that area. Okay, so Y bar equals the distance from the neutral axis to the centroid of the area. That's how we find the statical moment. There was another cartoon for that. This is essentially the same cartoon, except it's below the neutral axis. In some cases, in the problems, they have you plotting the shear stress distribution versus distance from the neutral axis. And then this is how that one would look like. And then here is the final one. This is example 14.9, and this is what the shear stress distribution would look like. Okay, that's the end of this movie. Thank you.